Every car panel, water pipe, lamp post, and truck wheel started life as flat steel. Bent into shape by hydraulic presses most people will never see in person at all. Some of them weigh 320 tons. Some squeeze plate as thick as a phone book. Each shape was engineered to resist what the press is doing. Watch these hydraulic presses at work. The destination might surprise you. Welcome to a world where 1,000 tons of steel bends like clay, where machines the size of a house squeeze cold metal into shapes that look impossible. And the only thing standing between flat plate and finished product is hydraulic pressure measured in numbers most people never have a reason to think about. Before any of those presses can flatten, bend, or roll anything, somebody has to build the frame, the gantry, and the lifting equipment moving material around. That work happens in factories that look nothing like the ones making the parts. Heavy steel beams arrive as raw stock. Workers align, secure, and precision weld plates into rigid crane structures and box girders that eventually carry tens of tons overhead. The kind of girders swinging molten ladles in a steel mill or lifting a pressed car panel off a die. Component assembly follows. Wheels, gearboxes, and electrical control wiring get measured, fine-tuned, and routed inside clean stations. Major bridge crane parts integrate. Safety specs go on next. The 15-ton finished cranes lift inside the factory to verify smooth functionality before flatbed trucks haul them under heavy tarps, heading toward the press shops where the squeezing begins. A 2,000-ton hydraulic press shapes a car door panel in roughly 4 seconds, and that one cycle replaces hours of hand rolling, welding, and reshaping. Robots feed flat sheet into the die. Hydraulic force drives the upper die down hard. The finished panel lifts out, still warm to the touch. A machine flattens a car panel in 4 seconds. What happens when the job isn't flat? When the shape has to curve in 2 directions at once? Bending a thick steel pipe. Actually bending it, not just pressing a curve onto it, takes a different approach. Heat the pipe until the steel softens, then bend the heated zone alone. Hot bending starts with the mother pipe arriving for inspection. The pipe loads into an induction bending machine, where localized induction heating glows a narrow band cherry red. Only that band bends. The rest of the pipe stays cool and stiff. The bend forms along the specified radius. Why is this hard? Bend a cold, thick wall pipe and it kinks, flattens, or cracks every time. Heat the wrong section and the pipe ovalizes beyond tolerance. The induction coil keeps the heat zone tight. Heat treatment then relieves residual stress. Destructive tests confirm mechanical integrity, magnetic and ultrasonic testing check flaws, and the ends bevel for field welding. Cold forming a ship hull panel into a saddle shape, curved both ways at once, is one of the rare jobs in heavy industry where the operator's eye matters more than any number on the control panel. A doubly curved surface follows no formula a CNC can read. The press has to feel its way. The flat steel plate enters the cold forming press. The operator commands the upper ram to apply force at specific points across the surface. Each press cycle pushes a little material, a little further than the last. The plate moves back and forth under the ram, picking up a primary curve along one axis. Visual inspection between cycles tells the operator how the steel is responding. This is where forming gets complicated. A saddle curves down along one axis and up along the perpendicular axis simultaneously, opposing deformations that fight each other inside the steel. The press has to pull and squeeze in alternating zones to create both curves without cracking the plate. Wooden or metal templates lay over the surface to check accuracy. Where gaps appear, the press makes small, corrective hits. Curved hull panels are one challenge of their own. Bending a structural steel channel, flanges out into a 1,400 millimeter closed ring, is another challenge. A 3-roll bender slowly cans the 18P channel through pass after pass. The center roll presses down. The outer rolls feed the steel through. Each reversal tightens the radius slightly until the two ends meet in a perfect closed ring. Bending an HEA 650 beam the hard way, through its strongest axis, is exactly the bending direction the beam was engineered to resist. The structural shape that holds up factories and stadiums resists every reversal of the rolls. The angle roll grips the beam between 3 large hydraulic rolls. The CNC controller calculates the bending cycle, drives the press roll incrementally, and reverses the feed rolls in rhythm. The HEA 650 curves smoothly without web twist or flange distortion. How does one machine bend a UPN 400 the hard way, an HEB 550 the easy way, and an IPE 600 back to the hard way without changing setup between every single operation it runs? Independent direct drive on each roll. 6-direction lateral guide rolls integrated. A universal hydraulic pulling unit holds the beam against twist. Same machine, different beam, same accuracy. The geometry adjusts itself to the steel. A 3-roll bender doesn't just handle pipes. The same hydraulic frame works square tube, rectangular tube, solid square stock, round bar, UPN channel, IPN profile, T-section, angle iron, and flat bar, usually with only a roll change between jobs of any kind. Each lower roll adjusts independently, which sounds like a small detail until somebody needs a smaller diameter than a pyramid bender can physically produce on its own. Asymmetric roll positioning electronically controlled lets the same machine roll a tight architectural curve in the morning and a wide structural arch in the afternoon. Same operator, same shift, same press. The machine handles horizontal and vertical work without extra accessories needed. Lateral corrector rolls control bending direction continuously. Straightening rolls handle angle iron without flange twist. That's the quiet versatility behind every architectural arch, greenhouse frame, bridge stirrup, and bus shelter most people walk past every single day without noticing. Beams curve into structural shapes. Turning a swimming pool-sized plate into a walk-in pipe needs a different machine entirely. Bent beams hold buildings up overhead. Rolled pipes hold something far more dangerous on a daily basis: pressurized oil, gas, water, and chemicals flowing across entire continents underground. Pipe rolling starts with flat plate, and the heaviest plate any rolling mill on the planet handles routinely. AFACCIN 3-roll bending machine takes plate up to 120 millimeters thick, up to 3,000 millimeters wide, and rolls it down to a finished cylinder with a minimum diameter of 1,400 millimeters. That's a cylinder you could walk inside without even ducking, formed from plate weighing roughly as much as a small car. How big can a single rolling machine actually get on the shop floor today in real life? This 320-ton 3-roll Haisler installed on a custom foundation deep enough to anchor the machine against its own working forces under full pressure operation. A 43-ton steel plate, 150 millimeters thick and 2,230 millimeters wide, rolls down to a finished cylinder 5,000 millimeters in diameter. Edge preparation comes first. Both sides get trimmed and beveled so the seam closes clean. Submerged arc welding then fills the joint with 2 wires feeding simultaneously, doubling deposition speed and finishing the seam in half the time. Offshore wind foundations and FPSO pile sections don't tolerate seam defects. What fails 100 meters below sea level isn't getting repaired with a service truck and a torch in the morning, or any morning afterward in the working year ahead of the operator. A 4-roll plate rolling machine handles a 100mm thick chrome molybdenum plate of high-yield strength steel, plus a thinner 30mm plate intended for an FPSO pile foundation. Both run under user-friendly controls, translating into capacity the previous machine couldn't deliver. Pipeline production runs at API standards, and API standards leave no margin for shortcuts or any compromise of any kind here. The 3-roll HAV-2P handles pipes up to 12,000 millimeters long with 3 motorized driven rolls, anti-deflection on top and bottom rolls, and automatic pipe ejection. That's the kind of automation turning a single plate into a transmission pipe ready for welding in one continuous cycle. Pipe rolling shapes one heavy plate at a time slowly. Roll forming does something completely different from that. It never stops running between coil changes. A roll-forming line for purlins runs C, U, and Z profiles interchangeably, with adjustable base width from 80 to 300 millimeters and flange height from 30 to 80 millimeters. Pre-punching holds tolerance to ±1 millimeter. Profile change from C to Z happens through motorized roll repositioning. No shutdown, no swap out. Just one button press. Rolling a 4.5 meter diameter cone, wide at one end, narrow at the other, is roughly twice as hard as rolling a cylinder of the same size on the same machine. A cylinder has one radius along its length. A cone has every radius between 2 endpoints, distributed along the same plate. The plate enters the rolls cut to a developed pattern that looks nothing like the finished part. The bottom rolls tilt asymmetrically to feed the wide edge faster than the narrow edge. As the cone forms, the operator constantly adjusts roll position to keep the geometry true. One plate, one heavy machine, and one finished pipe section. Now imagine a factory that never stops producing. Thousands of meters per shift, every shift, never a pause. A pipe and profile factory running at full tilt doesn't look like one machine doing impressive things. It looks like one continuous river of steel. Steel coils enter the slitting line at the front. Material straightens, cues, and feeds into the roll, forming stands that convert flat strip into round tube or square hollow section. Each stand bends the strip a few more degrees than the last until the final pass closes the section completely. High-frequency welding then seals the longitudinal seam. The pipe runs straight through the welding head at production speed. No stopping, no jigging, no rework. Heat treatment immediately downstream relieves welding stress and stabilizes the steel's grain structure for the working life of the tube. What's the bottleneck on a line like this? Coil change. Every time the feeding coil runs out, the line either stops or runs through a flying splice that joins the new coil onto the tail of the old one without interrupting the flow. Operators time those splices the way pit crews time tire changes. Automated measurement, surface inspection, and length cutting handle the back end. Finished pipe bundles, palletize, label, and load, and the line never actually pauses. Roll forming bends cold steel into shape. Aluminum extrusion does something stranger and harder to picture. It pushes solid metal through a hole and makes it come out the other side as a shape. The process starts with die design. Engineers draw the cross-section the customer wants, then build a steel die with that profile cut through it. Aluminum billets, solid cylinders. Heat to roughly 450 degrees Celsius. Soft enough to flow, but not melted. Then the press squeezes. A 1/100-tone hydraulic press drives the heated billet through the die at high pressure. The aluminium emerges on the other side as a continuous extrusion. taking on the die's cross-section perfectly. Window frames, heat sinks, structural sections, automotive trim, all from the same basic process. Why does it work? At 450 degrees Celsius, aluminum behaves like stiff toothpaste. Push it through a shaped opening and it flows. Cool it back down and it locks into shape with full structural strength. Cooling immediately downstream uses air or water. Stretching removes residual stress. Cutting to length follows. Aging ovens then build in the final hardness. Anodizing or powder coating finishes the surface. The plant runs 4,500 metric tons per year. Roll forming and coil processing equipment runs the back end of the entire construction supply chain, and most people have never even heard of it. CAD design feeds CNC machining. Plasma cutting prepares phosphor. Roll forming stands shape continuous strip into roofing profile and structural sections at high speed. Changing roll profile without changing the actual machine. That's the trick most fabrication shops would pay any amount of money to get right every day. Operators add or remove specific spacing rings on the roll shafts to switch profiles between small outside corner, ridge cap, minor ribs, and a handful of additional configurations on the same line. 7 passes reconfigure to form one profile, 6 passes reconfigure for another, all on the same line. No teardown, no replacement rolls, no overnight downtime. Producing the standard 41 of 41 channel framing, the kind quietly hanging the electrical conduit, the HVAC, and the cable trays in every commercial building over your head right at this moment. Runs at 10 meters per minute through a continuous high-speed line. Steel strip uncoils, levels, and forms through the successive roll stands. Pre-punching adds the slotted holes that make Unistrut universal across every single trade. Servo-driven flying cutoff matches the line speed exactly, cutting each finished length without slowing the flow. Continuous lines deliver kilometers of profile every shift. The next chapter operates on the opposite end of the spectrum. Heavy presses that work one massive part at a time, and each part weighs more than a loaded delivery truck. A 3,000-ton hot-forming press shapes the dished heads that cap pressure vessels in oil refineries, power stations, and chemical plants. Picture a steel disc the size of a backyard pool, heated cherry red in a furnace, craned onto the press bed, glowing with enough radiated heat to make the camera lens shake. How does pressing the head get done without cracking the plate? Heat is half the answer. At forming temperature, steel flows like stiff clay. Cold steel of that thickness splits on the first stroke. Pressure is the other half. 3,000 tons distributed evenly keeps thickness uniform. The upper die descends. The disc folds into the bowl-shaped lower die. And the whole room briefly looks like a sunrise. Multiple press cycles redistribute thickness, smooth the surface, and finalize the bowl geometry. Then the upper die lifts away. The finished head, still radiating heat, glowing dull red, lifts off the bed and heads to controlled cooling. A dished head, straight off the press, still has a raw outer edge. Turning that raw edge into a structural flange, bent inward to exactly the right radius, smooth all the way around, is a separate job done on a different machine entirely. The preformed head sits on a rotating bed. Hydraulic rolls press the rim inward as the head spins. Each rotation shapes a few more millimeters of the flange profile. Watching a multi-tone steel cap spinning at speed while machines bend its edge inward. That's not something most people get to see twice in life. Numbers tell the rest of it clearly enough. The dished head enters flanging at 4.5 meters inside diameter and exits at 4.3 meters. The rim has been folded inward by 100 millimeters on every side. Minimum thickness after forming holds at 36.6 millimeters around a circumference of 13,502 millimeters. Pressure vessel work covers the bowl shapes. Long structural plates. Too long for any single press brake on Earth. Need another solution. 2 press brakes working in synchronization, sharing the load between them. A tandem of a 1,000-ton brake plus an 800-ton brake gives 1,800 tons of combined force distributed across a plate length neither could handle on its own. 2 giants pressing one beam in unison without either taking the lead, and the choreography behind it is invisible from outside. What stops the plate from twisting halfway through the bend? CNC synchronization. Both rams descend at exactly the same rate. If one moves a millimeter faster than the other, the plate twists and the part heads straight back to the scrapyard. 1 plate, 2 presses, 1 perfect bend. And a hidden corner of industry the public almost never gets to walk through in person. Giant structures don't get the spotlight alone. The same hydraulic logic feeds smaller industrial parts most viewers have never seen up close. Screw conveyors move grain, cement, plastic pellets, and chemical powders inside every processing plant. Hangers hold the screw sections perpendicular, and misalignment shreds the screw in months. Forming a screw flight by hand used to take an experienced operator 5 minutes per flight, and the final result was never guaranteed. A hydraulic flight former does the same job in under 60 seconds, every flight identical. Hydraulic pressure turning a 5-minute craft into a 1-minute machine task. Industrial screws hide inside factories. The next chapter of hydraulic power hides inside your own street. Hydraulic pressure travels from the press shop right under your feet. Ductile iron pipe, the kind carrying drinking water under American cities, gets cast under inspection at every step. Visual checks for defects. Weight, wall thickness, bell and spigot dimensions measured against AWO standards before a pipe ships. How come ductile iron pipes have a bumpy outer surface? The mold is deliberately peened. A carbide-tipped punch creates the pattern, catching molten iron and inoculant dust to help the pipe release. Standing inside a ductile iron foundry feels nothing like a factory tour at all. Cherry red ladles swing overhead. Sparks fly from spinning centrifugal molds. Operators in heat-resistant gear monitor pours of molten iron at 1,500 degrees Celsius. Every casting cycle a controlled fireworks display feeding water into city pipes around them. Pipes carry water under the streets. Pressed steel rims carry the trucks rolling above them. The wheels on every commercial delivery truck, agricultural vehicle, and industrial trailer started life as a flat steel disc punched out of a coil, then bent into shape by high-tonnage hydraulic presses. The process starts with engineering. CAD models define the rim profile for each vehicle class. Raw steel sheets feed into presses that cut and shape circular blanks ready for forming. Then the heavy work begins. Rim forming sends each blank through press stations and automated rollers, bending the rim profile into its final cross-section. Each pass tightens the curve until the wheel takes shape. How does a pressed steel rim hold up to decades of load and impact? Material grade and process control. Welding joins inner components to the outer rim. Spot welds and structural seam welds fuse the assembly. Final turning trims excess material. Electrostatic powder coating sprays the rim. Red, yellow, green, white, black. And heat curing locks the finish in. Hydraulic machinery presses bearings into the hub. Tires mount and ship. One trip to the press, decades on the road, and every cycle starts again. Step back from the machines for a minute. What's actually getting bought and sold every time one of these presses runs? Speed. A 1,000-tone dishing press with a 27-tone CNC manipulator handling cold blanks up to 9,100 diameter cuts cost per finished head. Every second the RAM saves becomes another head this week, another order shipped, another reason a buyer chose hydraulic over the alternative entirely. Here's the discussion a lot of metal forum threads run aground on. As machines get bigger and CNC gets smarter, does skilled bending know-how disappear, or do shops actually need it even more? Cold rolling 38mm plate at 2,440 wide still asks the operator to read the steel by feel. Thanks for watching. Stick around. The next video covers a job that sounds impossible until you see how it's actually done.